Do you often encounter waveform oscillations, device breakdowns, or even equipment damage when testing silicon carbide and gallium nitride? Common mode interference under high frequency and high voltage is becoming an invisible killer in the testing of third-generation semiconductors. The optical fiber isolated probe, however, acts like a signal translator, building a bridge of light between the probe front end and the oscilloscope. It transmits high-voltage signals to the oscilloscope through photoelectric conversion. During measurement, the front end of the probe captures the original voltage signal, which is immediately converted into a pure optical signal by the built-in electro-optical converter. This beam of light is transmitted via optical fiber. Since optical transmission cuts off all electronic circuits, even the strongest common mode interference signals cannot form interference loops. Upon reaching the receiving end, the photoelectric converter converts the optical signal back into an electrical signal and sends it to the oscilloscope. In this way, the optical fiber isolated probe successfully extracts high voltage and floating ground signals from cluttered industrial field signals safely and accurately, presenting the true signal waveforms clearly. Next, we will use Micsig's MH068 model 1 GHz version oscilloscope, along with the DP1502 and optical fiber isolated probe MOIP350P. Test the gallium nitride substrate to demonstrate the excellent performance of the optical fiber isolated probe. The end with the BNC interface is the optoelectrical converter. On its side, there are an automatic calibration button and a range switching button. The other end is the electro-optical converter, which is powered by laser. Connect the attenuator and connect the end of the attenuator to the signal under test. Before the optical isolation probe is connected to the signal, set the oscilloscope's attenuation ratio to match that of the attenuator. Set the input impedance to 50 ohms and press the Cali. Connect the attenuator to the MMCX female socket of the gallium nitride substrate. Measure the upper tube signal of VGS on the substrate. Set the common mode voltage to 20 V. Enlarge the waveform. It can be seen that the waveform is relatively stable with little oscillation. We increase the common mode voltage to 300 V. It can be seen that the change of the Miller plateau of the waveform is very small. We save the waveform under the 300 V common mode voltage. Facilitate comparison with the voltage measured by the differential probe. High-voltage differential probes have lower common mode rejection capability than optical fiber isolated probes in the high-frequency band. Measure the VGS signal at the same point using a high-voltage differential probe with a common mode voltage of 20 V. In the Miller plateau section, the signal oscillation is relatively large. Increase the common mode voltage to 300 V, the signal oscillation gradually increases, and the waveform is almost unviewable. Next, when we check the VGS upper tube signal measured by the optical fiber isolated probe, we can see that compared with the differential probe, the signal has less oscillation and displays a more authentic signal. The key here lies in two words: photoelectric isolation. The optical fiber isolated probe completely cuts off the common mode interference path through optical fibers, achieving ultra-high common mode rejection.